In this exercise, we're going to go ahead and look at fitting a second order plus dead time constant equation to some actual data. So we have fit parameters kp and tau p, and we have a parallel process going on here. Here we have, as the process goes along, two processes happen, and both of those combine to form our output. We have a second order response with 0.05 second intervals and an input change of 2. And so with that, we really have just two variables. We have, if we think about our system really quick, we have our u, which is equal to 2, and we have our two gains. So y, as far as a deviation variable, will be equal to 2 times g1 plus g2. It's a g. And that should be equal to kp over tau s plus 1 minus 2 over s plus 1. And then we'll go ahead and we'll convert that to the time domain. So that's a y of t instead of a capital Y. Now you'll notice here, the only two things we don't know are this kp and this tau. As we convert back to our time domain, we'll notice both of these are kind of in similar forms. Both of these are in the form something over something s plus 1. Except this tau is an implicit 1 here. So that equation is equal to 1 minus e to the negative t over tau. It's a tau. And then the top part, that's going to be a 1 over that, and so the magnitude here is going to be multiplied here. And I'll note right here, that's the g, so there's going to be 2 times all of this. So the magnitude here is going to be, we'll have two separate things, but then magnitude for one of them will be 2kp, and the other one will be negative 2. So I'll do some dots so that I make it clear, or a comma. So let's go ahead, let's look at how we would do this and fit it. So the first thing to do, we notice this is the fit of our data. We have a step change of 2, and our response is about 2. So we're going to go ahead, we'll read it from this second order link here, and we'll read it into our matrix where we have column matrices for time and y, our output. So the first thing we want to do, this is our Laplace form right here, as we mentioned before. I'm going to go ahead and make a function called ysim. This ysim takes arguments t as well as kp and tau p. Then it will output 2 times kp times 1 minus the exponent of negative t over tau p. And that 2 is coming from that magnitude. And then negative 4, because we have the negative 2 up here, times the 2, which is the input. So negative 4 minus exponent of negative t, and that's because our tau is 1, so dividing by 1 we don't even have to write that. Then our objective function is going to be take some p for parameters. What it's going to do is it's going to distribute that into ysim, which is going to take time, p1 and p2, so it's going to input that kp and that tau p, and it's going to subtract that from this y we have from our data, and it's going to return the sum squared error of the two. Our guesses, we'll just go ahead and guess a 1 for our kp and a 1 for our tau p. And I guess the 1 is going to be off by quite a bit, but it's a good place to start. Nice thing is object fmin search, we don't have to pass any constraints. And then we'll go ahead and unpack the results afterward, and then we'll graph them. So we'll go ahead and we'll run this section. So we have our two function handles. And you'll notice here's our data in the blue dots, and then the dashed line, let's go down in our graph real quick. Y label, label, L-A-B-E-L, wow, that's so hard today, is going to be output. X label is going to be time, and then we need to do legend. So let's go ahead, run this section one more time. location we're going to say is southeast capitalized. Let's say southeast. So it's out of the way. There we go. So as we look at our graph, that's a little bit, the dots are a little bit small. Hopefully you can see them. Output, we go from 0 to 2. Our initial parameters take us all the way down to -2. So that doesn't work very well. But our regress parameters go ahead and keep us all the way in line. And what are our regress parameters? I think we need to take off the semicolons so we can see what they are. We'll run it one more time. It's a good sign with how fast Fmin's search works as well here. So our KP is equal to 3, our tau P is equal to 2. It fits very well. And there you have it. There's not much to this. We've done this before, creating a function. Here we've gone ahead and made lambda functions and function handles rather than the functions declared down below. And it's a simpler way to do the same thing we've done before. We take our functions, we create an objective function, and then we use fmin search to give our objective function and our guess, and return the optimal parameters such that our objective function was minimized. Hopefully that gives you a good idea of the process and it clears up any questions you may have. Let me know if you have any questions. I'd be happy to help.